Okay. So yesterday I assume you guys had your lab session on logistic regression. Any questions before we start new topic? Nothing? Okay. So let me remind you what we did yesterday. Obviously, the big focus on yesterday's lecture was logistic regression. Essentially, you have a problem where you need to make, where you have your target variable has two classes and you have a bunch of features, and using that features you want to predict which one of the class is the right class to bin the set of features. And GLM was a function that allowed us to do it. Using that particular function and doing things like step ASE, all of those were pretty standard things which we had learned in linear regression. The same ideas applied over here as well. The second half of yesterday's class we spent talking about how to evaluate the performance of your logistic regression. Okay. We talked about how, and we have touched upon this topic several times in the past, about as to how accuracy by itself is not a great metric. The metric that's often relevant is depending on the domain you're talking about, whether things like precision or sensitivity, so on. We introduced a bunch of new metrics yesterday. We paid special attention to kappa metric. That's often used in situations where identification of both the classes are important. So what you're doing in that case is that you are evaluating how much better are you compared to a random forecast. That's what kappa metric did. We talked about ROC curves. What ROC curve does is it measures the performance of the model for a whole bunch of values of thresholds. Okay, kappa, sensitivity, precision, all of them are for one specific value of threshold. Remember, logistic regression gives you a value of probability that this given member belongs to class 1. It's only giving you a probability. You need to decide after it gives you the probability, at what probability will you assign it to class 1 and below what probability will you assign it to class 0. That's the decision you need to make. It depends on the business situation that you are interested in. Kappa, precision, sensitivity, all of those guys expect you to make that threshold decision on the threshold, and then measures the accuracy. ROC curve, on the other hand, measures the performance of the model for all values of threshold. Okay, the area under the curve of the area under the ROC curve is therefore a metric on how the model performs on the whole over all the thresholds. Okay. We also talked about lift charts and gain charts, which are ideas that are often used in business situations. And those are easily explainable idea. You don't need to talk about this ROC curve and all that. So it finds applications in a lot of business situations, lift charts and gain charts. Towards the end of the lecture, we spent time talking about ideas of overfitting and underfitting. We talked about this notion of how we might choose a model that is too simple to represent the reality of the data, and what kind of errors happen. And when we choose a model that is too complex to represent the reality of the data, what happens? Specifically, when you are underfitting the model, what actually happens is you get a high error, but that error, we talked about how we can split up that error into bias, variance, and a random component. Bias part of the error is large when you're using simple models. Okay. You have a parabolic data, shape data, and you are trying to fit it with a linear model. there will always be error on one side. Okay, and the size of the error will always be the same on that particular side. So it's like biased, right? Your forecast will always be biased towards one side. So when model is simple, you have large bias. When you increase the complexity of the model, you end up decreasing the bias part of the error. But what might end up happening is that the variance part goes up. Variance part is essentially how much variation can there be in your error based on which test data that you're thinking about. That part is variance. So when the model is actually overfit for a given data, you encounter a test set. In the test set, you will see that the error is actually very large. Those ideas which we talked about, we also talked about another area, another topic, which is cross-validation, k-fold cross-validation. Those are ideas we'll touch upon again later today. Okay, so we are going to be talking about 3 topics: PCA, or principal component analysis, regularization, and naive-Bayes learning method. The first topic we are going to be talking about is principal component analysis. Okay. Now, this is I've mentioned only like 100 times that I use machine learning algorithms to predict stock price movements. That's my bread and butter. What I do for doing this particular, when I'm trying to handle this problem, is I use data about an individual stock. Let's say, for example, I'm trying to predict whether the index, Bank Nifty, is going to be moving up or down. So what I do is I use the past data of Bank Nifty. I look at what are the patterns, and there are different ways to quantify those patterns. I use all of those values of those patterns. I look at how the US market moved. When the US market, something crazy happens, that reflects on India as well on the following day. So I get data on the US market, and I try to quantify the patterns on the US market. Another thing that actually impacts Indian market is the dollar-rupee exchange rate. So I download the data of dollar-rupee exchange rate, analyze the patterns and how are the exchange rates changing. So I download that data, use that data. I also use data relating to the interest rate environment. Is that when the interest rate changes, when the bank, the RBI increases the interest rate, decreases the interest rate, makes changes like that, that impacts the stock price movements. So I download that particular data and have a bunch of variables which quantify the variation in those things. I also download the interest rate decisions made by the US banks. The US banks also have a big impact on the global economy. So by the time I download all of this data and look at the patterns of the data, I'm not looking just at the value of that data. I'm looking at how did the values change over the last 1 week, how did it change over the last 1 month, where is it right now relative to the past 1 year. When I take all of this and I create, for each one of these patterns, I create one new feature. Okay. By the time I've downloaded all of this data and created all the set of features that I want, I have something like 352 different features. Using these 352 different features, I'm trying to forecast whether tomorrow is going to be an up day or a down day. A lot of these features are going to be irrelevant. It might not really matter for whether tomorrow is going to be up day or a down day. A lot of these features are going to be similar. The movements of interest rates, the movement of the stock price movement between the US markets and Indian markets are to some extent correlated. Okay, when a recession happens, it's usually global recessions. All the global markets are tied. So many of these prices are correlated, and so each one of the 352 variables that are there might not have purely independent information. But it's 352 variables that are there. I can't manually look at each one of them and decide which one is related to what, right? Never is there going to be a situation where those two variables, two columns are going to be exactly same. That's never going to happen. What might usually happen is that 5 of these variables, when you add together, is correlated to this other 121st variable. Things like that might happen, and there's no way I can detect that just looking at by eye, right? So I just have to put all of those things and run a machine learning algorithm on it, hoping that the machine learning algorithm will not collapse because of large memory requirement, or worse, it might not collapse because some of them are linearly correlated. Those are all hopes. I've just put all of this, and let's hope that the machine can handle all of that. When I do all of that, and run the algorithm to try and predict whether tomorrow is going to be an up day or not, that algorithm takes about 14 hours to run. Okay, takes a long time to run. When do I get the data? Well, I get the data when the US market closes. US market closes at around 2:30 a.m. Indian time. I need to wait until the data gets published, say 1 hour, 3:30 a.m. I get all the data. I download all the data and start running my algorithm to train and figure out what is the right pattern. But that by the time the algorithm runs, it's 14 hours. If I wait until that, the end of the Indian market, a day gets over. So there is no way I can actually do this trading, right? So the question that was before me is, is there a way to figure out which of these 352 variables are important and which one of them are not important? Okay. One way to do it, we've talked about, is something like stepwise regression, right? Stepwise search. What do we do in stepwise search? For example, if you're doing backward search, start with all 352, run it once, then remove the worst one, and then run it again. Then remove the next worst one and run it again. Well, the very first time I'm going to run is going to take 14 hours. And I drop one and again run. Again, it's going to take maybe, 13.75 hours, and then run it again. It's not really an efficient way to do the process, right? So we learned stepwise regression as a useful way of cutting down the set of variables. But you know what? When you're dealing with large problems, it's not really practical. Okay? Are there better methods of doing it? Okay? That's the question. So we are going to answer this by, so this method, principal component analysis, helps us address this exact question. Okay? Is there a way to figure out what are the relevant variables? This is mathematically intense topic. Okay, it's going to require knowledge of linear algebra and matrix factorization. I'll probably be referring back to things that you've learned in your high school. You guys remember eigenvalues, eigenvectors? All of those topics are going to be covered. Okay, but I'm going to do my best not to invoke mathematics. Okay, I'm going to attempt to do all of this with just pictures. But in order to truly understand the process, mathematics is essential. So I would strongly encourage you to read up later. Okay, I don't want to do a better job of putting you to sleep than what I've been doing already. So I'm going to try and keep it to pictures and not force too much mathematics on you. But in case you have any questions later when you try to read up, feel free to ask me. Okay. So let's start with a simple example. Here is the y value that I'm trying to predict. And I have two features, x1 and x2. I'm not even going to tell you what this problem is. Doesn't matter. Okay, it doesn't matter what y is, what x1 and x2 are. The question I'm going to ask you is, can you tell me what is a relevant variable and what is not a relevant variable just looking at this? X1 is relevant, x2 is not relevant. Why? It's constant. There's no change at all in x2, right? When a variable doesn't change, you know that y is changing. When a variable doesn't change, it cannot be relevant in explaining something that's changing, right? This is the idea of principal component analysis. You guys notice that x1 had some variation. The standard deviation of that particular variable is 0.98. Standard deviation of x2 is 0. Remember, in recognizing that x1 was important, x2 was not important, you did not use any information about y. You looked at only the features, x values, and made the call that x1 was relevant and x2 was not relevant, right? This is because you spotted the variable which had most amount of variance in it, and you realize that the variable with very small amount of variance is probably irrelevant, right? That's what you did. Mentally, what you did was you had this picture. In your mind, you had a picture where what's being plotted is not y. We didn't look at the y value at all in making the decision. You looked at x1 versus x2. That's the only plot that you had in your mind. And you realized that x1 was changing, x2 didn't change. So in order to explain the change in quantity, you know what? I don't need x2 at all. x1 is probably a good model. No discussion came about whether we should use linear model, non-linear model, any other complicated thing. None of those discussions came out. Purely looking at variation, we made this call. Okay. Principal component analysis is this technique which only looks at the features that are available without looking at y, looking at only the features and talking about which features have large variance, which features have small variance, and making the call, and helps you make the call on what are probably relevant, what are probably not relevant. Okay, we are not paying attention to y at all. Again and again, I want to emphasize that. So in this case, all the variation was in x1, no variation was in x2. So we are going to say x1 is the dominant principal component of this feature set. Okay. In this feature set, what that means is that x1 is the component along which there is large variance. x2 did not have any variance at all. But you would have said, even if x2 had some variance, you would have said that x1 is the dominant principal component, x2 is the minor principal component. That's the term that you would have used. Let's look at another example. Y, x1, x2. Okay. Previously, we made a decision without looking at y. We are going to try take the same tack. Okay. Ignore y. Just look at the patterns in x1 and x2. The decision is not that easy this time, right? Both x1 and x2 are changing, right? Both x1 and x2 are changing. But when I plotted this feature set, just like before, x1 versus x2, it looks like actually x1 and x2 are perfectly correlated. Okay? In this case, we cannot just randomly ignore x1 or x2 because by the same logic. The logic we had was we are going to ignore one which had no variation at all, right? That's the logic that we had. Here we cannot do that. So what we are going to do is this. We are going to be clever about this and create new variables. Okay? The new variable that I'm going to create is capital X1 and capital X2. What is capital X1 going to do? Capital X1 is going to take these two variables, add them together. Capital X2, take the difference between them. You see that? I took two old variables and did a transformation. Two new variables I have. Linear transformation. When I did that linear transformation, what happens? You see that all the variation is on capital X1. X2 now has no variation. Now if I ask you which one is the relevant variable, your answer would be X1 is the relevant variable, X2 you can drop. Right? what have we done? By doing a variable transformation, we have found a way to drop off one of the features. The variable transformation is a linear variable transformation. I'm not doing any complicated nonlinear stuff. Just a linear transformation I'm doing. By doing that linear transformation, I have figured out which variable we can drop without, again, any reference to y at all. I'm just looking at x1 and x2, trying to play around with x1 and x2. Are there a set of variable transformations I can do which will make it clear which is an important direction and which is not an important direction, right? We can, because all you need is to do forecast, right? You're going to build a model now using x1. x1 versus y is the model you're going to do. Then, when you have to make forecasts on the new one, you know that the new data is going to come only in this small x1, x2 old variables. So I'll take them, add them to, now I know that that's the value of the capital X1, and then I'll use that to predict. Before making the prediction, I'll do the transformation again and then make the prediction. But my model building is much easier in this coordinate rather than in the original coordinate. So this is the coordinate under which I'm going to work. Right? Very good question. Is this only applicable to numeric? Obviously, I can do these transformations only for numeric. So we are going to talk about only numeric. But ask me this question at the end of the this topic again, if I don't address it. Yeah. It's not mandatory that x2 will be constant. I am just saying, in this case, I have figured out a transformation which will make x2 to be constant. So this is one of those nice cases, and I know that I can then drop off x2 and build only a model with one feature. Right? This is an easy situation that I have. So in this case, what actually this transformation did was it took a coordinate. So we made this plot: x1 axis, x2 axis. In this plot, I have my data points like this. Right? What that transformation does is effectively create new variables whose axis, that is capital X1 and capital X2. It took a rotated axis, and in that rotated axis, along X1 is the variation and along X2 there is no variation. That's what it did. Okay, it took the axis and rotated it, and when you rotate it, you again find that in only one axis there is variation. So that's what this graph is doing. The new variables are creating new rotated coordinate system. Okay, even if you don't understand this concept of rotated coordinate system, that's perfectly fine. You understand that a variable change allowed us to make to view the same data in a way so that you can drop one of the variables. As long as that idea is clear, it's fine. Now, sure. So what we have done, we are doing a variable change. Okay, x1 and x2, right? So in terms of this new variables, capital X1 and capital X2, I'm going to plot capital X1 and capital X2 here. What you find is that the value of X2 is 1. But value of X1 can be anywhere on that. All the variation is along X1, X2 is constant, right? What had actually happened underneath is that you considered a rotated axis. This was an axis. So if you had tilted your head and looking at it this way, you see that along this axis, the value is constant. Along this, along this axis, the values are constant. Along this axis, values are changing. Right? This process of you rotating your head is equivalent to a coordinate transformation or a axis rotation. Okay, that's what had happened underneath. Yes. we are just starting. You'll see what are the ways that come about. Yeah, you're thinking in the right direction. So this is the transform coordinates, right? X1 axis, X2 axis. Along X1 axis there is variation, and along X2 axis there is no variation. Now can you tell me what is the dominant principal component direction? Dominant principal component direction is the direction along which there is most change, right? Dominant principal component direction, therefore, is this capital X1 axis, where there is most change. Along X2 axis, capital X2 axis, there is no change. Everyone with me so far? Yeah.
So when we apply these transformations, do you apply them to variables that are similar, or because it might be a hypothetical. I'm struggling to find an example. Do we run the risk of changing the meaning of the?
We absolutely are changing the meaning. X1 might represent, think of the cars data set. We are trying to predict mileage per gallon with horsepower and what is the other one? Time taken for, weight and horsepower. So weight and horsepower. These are the variables with which I am doing. Okay. Now I have gotten new variables, which is a mix between those two. So the old meaning no longer stands. So the original meaning, original interpretability that was there for your variables is lost when you do this coordinate transformation. That's a very important point. Glad you raised it. By doing this transformation, I lose the interpretability that I had of the original variables. But you know what? It allows me to solve problem more easily. So we are okay with it.
When it comes to transformation, it makes sense. You have to, again, reverse this.
We could do reverse the transformation, and we'll talk about how to reverse the transformation as well. That also brings about another important point. When I'm saying here, let's say we think about mileage per gallon, weight and horsepower, I'm creating a new transform variable, right? The transform variable is doing X2 minus X1. Am I allowed to do that? Am I allowed to subtract weight from horsepower? I can't do that, right? I can't mix two different variables, right? It makes no sense to mix two different variables when the units are not the same, right? So what I need to do before any of this activity, principal component analysis activity, is to standardize the variable. Make them all dimensionless quantity. How do you standardize the variable? Find the appropriate z-score, right? Convert them into z-scores, and then all of these transactions are valid.
But if standard there is no guarantee the same correlation exists.
It will absolutely exist. The correlation, standardization is you're changing the units. That's all you are doing. Changing units will not remove correlation.
I mean say between the factors.
Between the factors, changing the units will not remove correlation. Whatever was the correlation between a person's weight and the waist size will not change if I suddenly change measuring my weight in pounds. It's just a change of units. The correlation between my weight and my waist size will still be maintained. It's just a change of units. So standardization is nothing but change of units. When you standardize the units, what we are doing, standardizing, is choosing a set of units in which both these quantities are on the same order of magnitude. That's all I'm doing. And it's important to do standardization before we are going to do any of this procedure. Okay. I haven't told you what procedure it is, but you are seeing the hint of it. I'm trying to find new variables in which the variance along some directions are low, so I can drop it. That's where I'm going with all of this. With me so far? We've done 3 slides of material. Yeah. But it's important 3 slides. We need to make sure we understand this. Yeah.
We generally during the pre-process we do the standardization activity.
Right.
We do the standardization and at the end of the thing we have some model bits. The model consists of standardized factors.
Yeah.
Now if we are supposed to predict something,
Yeah.
we take the standardized variables and standardized factors and then predict the variables.
You can do it either way. You take the new variable that is coming in, you standardize it and apply into the same equation. That's one way of doing. But you can also convert the original equation back into the original variable. That is also possible. But what is normally done is whatever variables are given, you standardize it and predict. Use that to predict using the same model you develop. That's what is always done. Okay. So now over here, yeah. We are doing a linear combination. We are creating a new variable by making a linear combination. In this case, I didn't tell you how I got this linear combination, but I plotted the graph and it fell on a straight line. So I thought that subtracting them might make a good idea, might cancel out the correlation between them. So I subtracted them, and in this case, it actually worked. But we will come up with the actual method of figuring out what is the right transformation soon. Correct. We can do, for sometimes you might have to find 3 times x1 minus 5 times x2 might be needed. But we'll come there in a second. In this case, we realize that just doing a simple subtraction worked. So I'm showing you the concept behind it. I haven't told you how to find out for any general matrix yet. Okay, so in this case, x1 direction, we would say is the dominant principal component here. That's the direction along which most variation is there. Okay, so PCA is a method which allows you to identify the directions in which they have most variations are there. Okay, or equivalently, it can also be thought of as a method which allows you to identify directions in which there is least amount of variation so that you can drop them. Potentially, you can drop them from your analysis. That will help you reduce the number of features that you need to analyze the particular problem. Okay, so that's what PCA is going to do. Now,
you have least variation doesn't mean that it's not having impact on the target variable, right? So,
good point. We will come there. Generally, see, generally speaking, in this case, there is no variation at all on the on this direction. So there is no way it can impact the target variable. So now I'm saying, what if there is only small noise along that? The biggest variation is along this. So this must be the most important relevant variable. All of this is in the standardized directions, not based on units. In standardized directions, it looks like this one is not important, but this one is important. It's based on that hypothesis that we are moving forward. Okay, so here is another data set. This data set, again you see that x1 and x2 have high amount of correlation, but it's not perfect correlation like before, right? In this, for this data set, can you tell me, identify the direction of dominant principal component? Can you identify the direction of dominant principal component? Which is the direction in which there is most variation? Well, we already recognize that your principal component direction need not be this x1 or this x2. Principal component direction is the one in transformed coordinate where you are isolating the direction along which most variation happens. That's what we call as principal component, right? For this problem, can you identify for me which is the direction of dominant principal component? Yeah. The direction of dominant, this problem is very similar to the previous problem. The only thing is, if I find a transformation so that which will put my axis along this. Okay, one axis along this, another axis along this. So I take this coordinate system and rotate it like this. Okay, if I find a transformation which will put an axis along this, then that axis would be my dominant principal component. Agree? I haven't told you how to find the transformation, but if I find that transformation, that will be my dominant principal component. Okay, so this is the direction of my dominant principal component. This is the minor principal component. Unlike in the previous problem, in this direction there is a lot of variation. In the previous problem, in this direction there was no variation, but here there is some minor variation along this direction. Okay, the question now is, how do we compute this? How do we identify these axes? And how do we do the transformation so that in the transformed axis I can drop the minor principal component? The direction is irrelevant, right? I mean, we choose by convention this is positive and that is negative, but I could have put this one to be positive and that one to be negative. The meaning still remains the same, model still remains the same. The direction of the axis is pretty much arbitrary. Direction is pretty much arbitrary.
The magnitude tells us clearly, right? Why do we make the things?
Well, it tells you clearly. The magnitude tells you clearly because I drew a bigger line here. I chose to draw a bigger line here.
No, you see the scale. Here on the x2 scale, the magnitude is 6 units. On the x1 scale, the magnitude is 5 units.
Okay.
So that itself will tell.
Both are about the same. There is a variation of 5 units. Well, 4 units here and about 6 units variation. Both are about the same. It's not like completely ridiculous. One is like 5 times larger or 10 times larger, right? Both are of the same amount of very rarely will you find a problem where the amount of variation is exactly the same. Very rarely will you find that case. Both are of same order of magnitude. If I find the transformation which will put the coordinates like this, in that transformation this has lot of variation. This axis will not have much variation. So the question is, how do I find the transformation? Yeah.
What is the difference between this one and the step AIC? Because both of them tries to find out the significant variable.
It tries to find out, but step AIC uses Y and does a regression. Correct? It does a regression, finds out whether that regression has significance or not, and then drops one variable, then builds another regression, finds out whether that has significance or not, then drops one variable and keeps doing it. We haven't talked about Y at all. We are just looking at X's and trying to find the direction in which the component of X which has got large variation, component of X which has got small variation. That's what we are doing. Very good questions. Good questions. Yeah. So, again, this is similar to VIF is what you mean. Okay, yeah, because it was AIC and VIF. I was not sure which one. So, it's not similar to AIC in the sense that AIC measures how much information is lost in building the model. We are talking about the Y, how much information is lost in the Y. So, it's not similar to AIC in the sense that no reference to Y is being made. However, you are perfectly right. It's very similar to VIF. VIF talks only about the predictor values and it builds a linear model, take each predictor value, build a linear model with respect to the remaining one. Okay. So, you are absolutely right in your intuition. You have the perfect intuition about this, that correlations between those variables is very important. Okay. That intuition, do you understand what he is referring to? VIF values was again computed without talking about the Y value. We were only talking about the X values, and we tried to compute R squared for each one of those X value relative to the remaining ones. Okay, because that captured any correlation that might be there in the data, and I'm glad you're recognizing that this is also talking about correlations within the data. Okay, but we'll see if there is a way to connect that soon. Okay, so is everyone with me on the following point, in that this direction is a dominant principal direction, dominant principal component, and this is a minor component. Yeah. Thing is, I've done this plot. This was a two-dimensional problem, right? Y value, forget skip the Y value. X1, X2 are there. I'm plotting all of this, but there's no reason why the idea cannot be applied to larger dimensions, and it's applied to larger dimensions too. So here is an example in 3D. The original problem actually had 48 dimensions. This is one of those genetic human genome identification project data set. Here is, unfortunately, it's not, I don't have the data and I didn't generate the graph. It was just picked up from a website, so I can't make it brighter. I hope you're able to see. So you have a bunch of data points that are there. Okay, the data points are not uniformly spread out in space. The data points, from when you look at it from here, it's aligned along this particular direction, and when you rotate it to another view, you see that they're all along what might be termed as a dumbbell shape. Okay, this there is a cluster of points here, cluster of points here, that kind of thing. So in this problem, you would have said the dominant principal component will be along the dumbbell, right? And there is less variation along this one and along this one. And we might be able to drop one of them, whichever one does not have too much variation. And we can deal only with two variables, right? If we find the right transformation to rotate the data, we might be able to use only the variation in this and drop one of the variables which has got less variation. That's where we are going with this technique of principal component analysis. Okay. So the idea is, try and find the one that has got a variable which has got least amount of variance in it. And so as I mentioned, PCA is the way of identifying directions of largest to smallest variance. And once we are able to identify this specific direction, once you're able to find isolate the largest direction and the smallest direction, hopefully we can drop off the smallest direction and have a simpler model. All of this without even looking at the Y yet. Yeah, you had a question.
Instead of dropping that altogether, does it make sense to try and take that variation into the dominant variable?
We'll come there. When you drop one, you're not completely losing information. We'll come there in a second. Okay, so here we go back to the intuition that you had about the problem. This is related to correlations between variables. That is where it's related to. So to find the transformation, we need to use that information. Okay, not just correlation. We are talking about which direction has lot of variance, which has less variance. We're talking about that, right? So the concept that actually we are seeking is covariance, not correlation. So what we are going to do is take these variables and write out its covariance matrix. Okay. What is matrix? I mean, we talked about covariance as individual variable, right? Well, covariance matrix is, if you have 10 variables, covariance matrix contains pairwise correlation between all of them, pairwise covariance between all of them. So this is the covariance matrix. Along the diagonal is covariance of x1 with itself. Off diagonal is covariance of x1 with x2. Okay. We can, I'm hoping that at least it's intuitively clear why we need to be dealing with covariance matrix. We might not know what to do with it yet, but it's important because the variable transformation we are going to be doing relies on the fact that there might be correlations between features that we are using. Yeah. Absolutely. Covariance is, so everyone remembers correlation? Good. So covariance is just a scaled, standard deviation of 1 times standard deviation of 2 times correlation of x1 and x2. Correlation is a number without units. It doesn't have any reference to units. Covariance has units. It has units of x1 times x2. Okay. So covariance is a number that has information about the variance inside. It has the same units as variance because standard deviation of 1 times standard deviation 2. So it's like almost standard deviation square. So it's got the same units as variance over there. Okay. I have this data. I wave my hands and try to convince you covariance is important in this analysis. I'm going to go ahead and compute the covariance. So covariance in R you compute with the COV command, covariance of between those two values x1 and x2, and I get a matrix. Okay. Notice covariance of x2 comma x1 will be same as covariance of x1 comma x2 because correlation does not matter. The order doesn't matter as far as when you're talking about correlation. So covariance also the order doesn't matter. So it's a symmetric matrix that we have. Yeah. So we're going to be talking about matrices and arrays. This is and matrix manipulation and array manipulation. How many of you have been exposed to arrays and matrix after high school? Not bad, not bad. I recently got this message from about definition of array, and I thought, you know, it's actually most people's emotions about arrays are, you know, very well captured. The only array you still remember is that array Rupesh, right? That's the only array you remember. But there are some ideas of that you learnt in matrices and arrays. I'm hoping you still remember. One of them is the idea that matrix is used as a way of transforming vectors. Okay. So here is a vector 1 comma 1. I can plot this vector on an axis, on a normal coordinate system axis. This point would be over here, right? So this 1 comma 1 is actually referring to the direction of the vector. Okay, it's talking about the final point which has 1 along x1 axis, 1 along x2 axis. So this is that point. This vector is referring to, that symbol is referring to a vector pointing along this particular direction. Okay, I hope you guys remember that fact. When I take our covariance matrix that I had before and act on this particular vector, I get this vector. Can you tell me what direction this will be in? So negative x1, so negative x1, positive y, so somewhere over here. Okay, so what I have is this vector. So what the matrix did was it took this vector, acted on this vector, and rotated and stretched that vector to this direction. Okay, this is what matrices do. This is one simple way of interpreting what matrices do. Matrices are transformations which rotate vectors and stretches them. Okay, that's the effect of a matrix acting on vector. Now, for every matrix, there are, however, some very special directions. Like for this particular matrix, the same covariance matrix, there is this very special direction where its action is only stretch action. So this particular matrix, this particular vector, negative in the first variable, positive in this one, is a variable that's here, that's this vector. When I apply this matrix on that particular vector, I get another vector which is 5.51 times the original vector. So this A vector got just stretched. So there are some very special directions of vectors where when that matrix acts, all it does is stretching, no rotation. Okay. For every matrix, it will be a different vector, different direction, which is this very sacred direction where no rotation happens, only stretching happens. Okay. This is this kind of direction, the direction in which vectors are only stretched but not rotated, are called as eigendirections or eigenvectors. That's the meaning of eigenvectors. It's that special direction for the given matrix. When that matrix acts on that direction, no rotation happens, only stretching happens, either stretching by increasing or stretching by compressing. That particular direction is called eigendirection. If you have a different matrix, for that different matrix it will be a different direction, but every matrix has some special directions where there is only stretching, no rotation, and those special directions are called as eigendirections. Okay, and the amount by which the stretching happens is called as eigenvalue. Clear? I hope it's coming back, all of these ideas. So the picture that you need to have is this. You had different points in the coordinate system. Okay, the red points are the different points in the coordinate system. Each point, when matrix acts on each point, it gets shifted to another point. Okay, so you can think of this grid of points, the red grid of points. When the matrix acts, it got transformed to these blue points. Okay, each point moves to a different location. However, there are some special directions. Points which lay on those special directions might have gotten stretched or compressed but did not get rotated. All other points would have gotten rotated and stretched, but along these two directions, points do not get rotated, only stretched, and those two directions are what we call as eigendirections. Okay. So you understand this picture, right? So I shouldn't ask it that way. Should I explain this picture again? Okay. Here I have a red grid, okay, on a rectangular grid of points. Each point I can represent by an array, by a vector, right? When I apply the matrix on that each point, that point will get rotated and stretched, right? So generally this red matrix, every single point on this red matrix gets rotated and stretched, and into this, let's say this blue matrix. Okay, rectangles no longer remain rectangles, they become diamonds or whatever. It's a linear transformation, that's what happens. But one of the property of this transformation is that there are some special directions along which, and that special direction for this happens to be this and that, where only stretching happens. So if you notice, this red point got stretched to that point. This red point got stretched here. It didn't rotate. It's along the same axis as it originally was. So for that, this matrix, for whichever matrix this picture has been drawn, yeah, the eigendirections are represented in the green and the black. Those are the eigendirections. In terms of matrix notation, eigendirections this process is represented by this formula. A is the matrix you are talking about, whose transformations we are interested in. It acts on some special vector x. When it acts on it, its effect is to give a scaling factor times the same vector again. This lambda is called as the eigenvalue, which measures the stretch or compression in that particular direction, and that x is that special direction in which it happens. It happens only for some special directions, not for any general vector. Clear? Okay. what I've done is defined to you eigenvalues and eigenvectors. The
If we have A and X are two different matrices,
yeah.
and we had a product and we got this lambda times of matrix.
Let me just this thing. I just want to make sure that the language we use are the same. A is a matrix, X is a vector. So this could be a 3 by 3 matrix. X will be a 3 by 1 vector.
Yeah.
Okay. Now.
So when we multiply that,
Yeah.
and then we get another
Vector.
Yeah, vector. We can always find some lambda.
No.
No, we can, right?
So here. So this matrix got applied to that particular vector.
Right.
And I got a new vector. Can you find a lambda where you can write it in terms of 1 comma 1, some number times 1 comma 1? You can't. And you can see it pictorially better. This was the vector. New transformation changed it to this. It's not the same direction, which is why you can't write it as a scalar times that original vector. It can work only for some special directions. Only for some special directions. And that's why those directions are, special, and they are eigen directions or eigenvectors. Okay?
We started the topic by saying what is that size.
Correct.
And then we started talking about covariance.
Correct. Yeah.
How do you reconcile both?
We will come there. Just I'm referring to that we need to make all units the same, but we'll come there in a bit. You're raising good points. We'll come there. So what we are doing now is the eigenvectors are the principal component direction. The direction of the eigenvectors turn out to be the direction of the axis along which you have maximal variance. The value of the eigenvalues that you got, which refer to the magnitude of stretch, is nothing but in the new coordinates, what is the variance along that axis? That's what the eigenvalues are. Okay. I'll come back and we'll see that this is true in a second. But the whole reason we suddenly held the covariance matrix and moved on to talking about eigenvalues and eigendirection is that we said that we need to find a special direction in which suddenly we can decide which values to drop. Turns out eigendirections are that special directions in which the values are separable into directions of large variance and directions of small variance. Okay. So in this particular matrix we talked about, our covariance matrix that we talked about, I can find the eigenvalues and eigendirections by this command eigen. Okay. So I had two options. One was do the math and show you how to compute eigenvalues and eigendirection. I wasn't sure anyone will be awake, so I'm just showing you the final values of that. So eigenvalues turn out to be 5.51 and 0.03. Okay, two eigenvalues I got, and those happen to be the eigendirections. Okay. Now, do you know which axis, which coordinate will this? This is second quadrant. Yeah, this one. So remember how our data set looked? Like this, right? Our data set looked like that. Eigenvalue, the largest eigenvalue was along this particular direction. And how do you plot this vector? Which direction will be? Right? Negative x. So that's a vector that's along that direction. Okay? What about this one? Third quadrant, right? So those it's looking at this data spread and it's saying those are the special directions. One is along this axis, the other one is